Hello there, Mr. Sutton here with the BC Calculus 8.5 Extra Practice Number 1 Solutions on polar slope and basic area. For this problem, we want the slope of the line tangent to the polar curve r equals 2 cosine of theta minus 1, where theta equals pi. So we need to express this parametrically in terms of x and y, and then we can do y prime of pi over x prime of pi to get our answer. So for x in general, we have x equals r cosine of theta. So in this case, we have x equals this r value, 2 cosine of theta minus 1, times the cosine of theta that's normally part of our x equals r cosine theta formula. And I'm going to simplify this a little bit before I take the derivative. So this will be 2 cosine squared of theta minus, if we distribute the cosine, minus 1 cosine of theta. Taking my derivative now, I've got a chain rule going on here. So this is going to be 4 cosine of theta times the derivative of cosine, which is negative sine of theta, minus, this is going to be negative sine of theta, but I'm already subtracting it, so it's actually going to be plus sine of theta. There we go. And then this is really negative 4 sine cosine. Well, we know that 2 sine cosine is equivalent to sine of 2 theta. So this is really negative 2 sine of 2 theta for this first term. And it definitely is worth simplifying that, just to not have to plug in so many different spots here. Okay, let me go ahead and find y now. Y of theta, that's in general going to be r sine of theta. So 2 cosine of theta minus 1 quantity times sine of theta. Distributing that before I take the derivative, we've got 2 cosine of theta sine of theta minus sine of theta. This expression here is equivalent to sine of 2 theta, double angle identity being used again. We get a lot of mileage out of that one on these problems. So now let me go ahead and take the derivative. And now the benefit of doing that little identity is I only have a small chain rule versus a product rule that's going to make a whole lot more terms than I want to deal with. So derivative of sine of 2 theta, that's going to be cosine of 2 theta times a tail of 2, so 2 cosine of 2 theta. And then sine becomes cosine, so minus cosine of theta. All right, let's plug stuff in. So dy over dx evaluated at theta equals pi. That's going to be y prime of pi over x prime of pi. So for y prime, we have 2 cosine of 2 pi minus cosine of pi. Down below for x prime, this is going to be negative 2 sine of 2 pi plus sine of pi. Back upstairs, cosine of 2 pi, that's really 1, so 1 times 2 is 2. And let's see, cosine of pi is negative 1, but we're already subtracting it. So we have 2 plus 1 upstairs. And then downstairs, sine of pi or sine of 2 pi, either way, that's 0. It's the y value at 360 on the unit circle. Sine of pi is also 0. So this is a grand total of 0 down here. So this then ends up being undefined, dne, which means our slope doesn't exist. That's going to be choice D. For this problem, we want the slope of the tangent line for the curve r equals 2 theta at the point theta equals pi over 2. So in general, for dy over dx of a polar function, we need y prime of the input over x prime of the input. To get that, though, we need x and y, so let's express this in terms of x and y. We have, in general, x equals r cosine of theta. So in this case, we can say x of theta equals 2 theta times cosine of theta. And I'm going to take the derivative of that now to get x prime. This is going to require the product rule. There's no way to get out of this. So it's box and ribbon time. But these aren't too bad. I've got factors of 2 theta and cosine of theta. Derivatives there, we're just going to have 2, because we're taking the derivative with respect to theta. So just 2. And then this is negative sine of theta. Using the ribbon to multiply that out, this is 2 cosine of theta minus 2 theta sine of theta. So we'll come back to that, but there isn't really too much else we can do to simplify it at this point. So now let's do y of theta. That's going to be 2 theta sine of theta, because this is y sine, or it's a r sine of theta for y. And then this is another product rule. So again, we have 2 theta, and now we have sine of theta, whose derivatives are 2 and cosine of theta. Using our ribbon to multiply those out, this is 2 sine of theta plus 2 theta cosine of theta. Okay, so this is going to be a little bit of a mess, but we're putting it together now. If I want dy over dx at pi over 2, that's going to be y prime of pi over 2 over x prime of pi over 2. So that's going to be this y prime with pi over 2 plugged into it. So that's 1, 2, 3 different spots we're plugging in pi over 2. And x prime of pi over 2, that's 2 cosine of pi over 2 minus 2 pi over 2 sine of pi over 2. So just be careful rewriting all this stuff with pi over 2 plugged in. And at this point now, I actually have to simplify it to get an answer choice. Sine of pi over 2 is going to be 1, so this is just 2 up there. And the rest of this craziness, cosine of pi over 2 is 0, so that zeroes out that whole second term. So we just have 2 in the numerator. So 2, and again, this is going to be plus 0. So downstairs now, cosine of pi over 2, we just said that was 0. Over here, sine of pi over 2, again, that's 1, but now it's being multiplied by this other part here. The 2's cancel, leaving us with a pi, so this is minus pi when all is said and done. So altogether then we have negative 2 over pi, which matches answer choice B. For this calculator-based problem, we have this figure above with the graphs of the line x equals 5/3 y. So this is an x equals f of y kind of situation. So that's this line right here. And we also have x equals square root of 1 plus y squared. So that's this this piece of a sideways parabola here. S is the bounded region. We want to figure out for part A the coordinates of this point P up here, and then dx over dy for curve C at point P. All right, so we need to figure out what P is and then plug it into the derivative of C with respect to y. So let's find this intersection first. I'm going to start to make my life a little bit easier by naming these two functions. So I'm going to call this first one f of y, so f of y equals 5/3 y. I'm going to call this other one g of y. So now I can talk about them individually without rewriting everything. And in general, I need to figure out where f of y and g of y equal each other to figure out this point. Now, I could actually set them equal algebraically, and I could solve that, but I'm going to use the calculator because this is a calculator problem, so, well, why not? So here I am on my calculator in my y equals, and I know this is an x equals f of y kind of situation, but I'm going to graph it as y equals f of x on my calculator because my calculator can actually find values. All calculators can find values if you graph it this way. Not every calculator can find functions like this right here. So if yours has that capability, good for you. Mine doesn't. So I know that when I go ahead and solve these now, all the x values and y values are swapped from the real function, but I'm going into this knowing that. So for my window, not really sure, they didn't tell us, but this is the x value 1 right here. So this intersection point doesn't look like it's going to be too far away from that. So let me do zoom 4. So there's our line, and there's our parabola. Now again, this is actually flipped over the line y equals x from the true function, but I just need to find the intersection because I know if I find the x value where these intercept, that's going to correspond with the y value that this point P actually has. And the x and the other y are going to be swapped as well. So let me do second trace intersect, and then just enter, enter, enter. So we get, on our graph here, we have 0.75 and 1.25. What that actually means is that these are intersecting at y equals 0.75. Oops, there we go. So I'll call that 3/4. And then if we plug that back in to get an x value out of that, 5/3 times 3/4, that matches what we see here. It's just going to be 5/4 for the x value. So we've got the point then 5/4 comma 3/4. So that directly answers the question of what is point P. All right. So now let's go ahead and do the other part of this problem. They wanted the value of dx over dy. So dx over dy for the curve is actually this g of y function here. That's what we have to use. Since this is a calculator problem, I'm allowed to just take the derivative of a function at a single spot. In this case, I'd be doing g prime of the y value at point P. So this would be g prime of 3/4 that I want to do. And let me just do that directly on the calculator. So on my main screen here, I did Math 8 to get derivative. I'm doing a dx here, and I'm using y2 because that's where I stored this 1 plus something squared function inside a square root. Evaluate that at 3/4, and that gives us a value of, well, this rounds off to about 0.6, so it's probably 3/5 at that point. For this part of the problem, they want us to set up and evaluate an integral with respect to y that gives the area of S. So to help me out here, I'm just going to rewrite the point I found in part A. We saw that P was 5/4, 3/4. And if I'm going with respect to y, that means my integral, I'm going to have to be going, let's see, this is from bottom to top. So at the bottom we have 0. At the top we have the y value 3/4, so integral from 0 to 3/4. And now the integrand here, it's going to be right minus left function if we're going with sideways rectangles here. So that means I have to have this function minus this inner function, which we're going to be doing basically based on how I defined them earlier. This curve here I defined as g of y. This line I defined as f of y. So this is going to be g of y minus f of y. All of that times a dy in there to really get proper notation. And now I just have to plug this in my calculator. So on the calculator, I've got my Math 9 integral from 0 to 3/4, and g I stored as y2, f got stored as y1, so there we go, dx. And that's going to come out to 0.347 if we round it off. There we are. On this part of the problem, they're telling us curve C is part of the curve x squared minus y squared equals 1, which is a hyperbola you might recognize that as. You could get that just by squaring both sides of the equation and subtracting the y squared, so that's kind of nice. We want to show that this equation can be written as the polar equation r squared equals all this craziness. Okay, well, the key on this is recognizing that x, in terms of r, x is really r cosine of theta, and y is really r sine of theta. If you know this key piece of information, we can just substitute r cosine of theta for x in this equation, and r sine of theta for y. So I can rewrite this as, this will be, let's see, r squared cosine squared of theta minus r squared sine squared of theta. All of that equals 1. And now I'm just going to rearrange this to get the expression that they desired right here. So I see that these both have a factor of r squared. I can just factor that out, leaving me with cosine squared minus sine squared inside. And then to get r squared by itself, which is what we have to do here, we just divide by cosine squared of theta minus sine squared of theta. So we have 1 over all the stuff in the parentheses. And that proves what they wanted us to set out and prove. For this last part of the problem, they want us to use the polar equation that we got in part C to write an integral expression with respect to the polar angle theta that represents the area of S. So basically polar area. Now notice that they said set up an integral expression. They didn't say evaluate it. So we're not really going to have to figure out any crazy decimals on this. We're just going to have to get the basic setup. Polar area in general is given by integral from a to b 1/2 r squared d theta. So we need to plug in values for a, b, and this r in here. Let's find our limits of integration first. So this is basically the angles that take us from here over to here along this curve. So we're starting down here at the angle 0. This is 0 radians right here. And what angle is this up here? We have an x and a y value, but we don't know what angle actually gives us this point right here. Well, to get that, we can actually use tangent. We know that tangent in general equals y over x. So we can use inverse tan of y over x to get the value of that angle. So then I'm going to call this theta sub q, or sub p rather. This is telling me the angle at point P, and that's going to be tan inverse of y over x, so 3/4 over 5/4. That gives us some angle, some decimal. I could find it on my calculator, but there's really no need because they just wanted us to set up an integral expression, which means as long as we have a constant plugged in for this upper limit of integration, I don't need to do more. This whole thing counts as a constant. So I'm going to just go ahead then with an integral from 0 to theta sub p. Now I also need to fill in a value for this r squared, and the key on this is in part C, well, we found r squared. It's 1 over cosine squared of theta minus sine squared of theta. R was essentially this curve here, so since we can represent r squared as this, that's what we need to plug into our formula. So when the dust settles then, we have the integral from 0 to theta sub p of 1/2 times all this craziness, d theta, and now I've got everything I need in order to satisfy the problem. I've got an integral expression, I've got constants plugged in for a and b, I've got an actual function instead of an r squared, so we're good to go. For this calculator-based problem, we've got this S region in here enclosed by r of theta, which is this crazy function, along the interval from 0 to square root of pi. We want to just start by finding the area of S. So I'm going to start by just plugging this in my calculator. For the first several problems, it actually doesn't matter whether you're in function mode or polar mode, but I'm going to put it in polar mode just so I can actually get my own graph here. If I'm allowed to use the grapher, I like to know what I'm dealing with. So I've entered the function in polar mode in R1 equals, and then let me set up my window to be just like theirs. So from 0 to, let me do the square root of pi, which is kind of a weird number, but hey, we'll roll with it here. And let me do zoom 0 just to see their version of my function here. So the reason it looks kind of weird is on my window, my theta step isn't maybe as precise as theirs is. I could get exactly what they wanted if I have a smaller theta step. So whatever, I'll just use, I don't know, pi over, let's say pi over 36. Doesn't really matter. Okay, let me try it again. And now I get a slightly smoother curve. Anyway, we're trying to find the area of S. So in general, we need to use our polar area formula. That's the integral from a to b of 1/2 r squared d theta. Well, a and b in this case is just going to be 0 and square root of pi. So we have the integral from 0 to square root of radical pi. And now the r is just this r of theta they gave us. So we're just going to do r of theta squared, 1/2 times that. And I just have to plug that in the calculator. So going back to my calculator, let me just quit out to the main screen. And I've got Math 9 integral from 0 to radical pi. Fun to enter that. And now in here I've got, let's see, 1/2. Whoops. Let's try this again. There we go. So 1/2, and let me do alpha trace to pull up R1, and we're squaring that. All of that gets a d theta. Enter. And we've got about 3.534. We'll take their word for it. So there we are. For this part of the problem, they want the average distance from the origin to a point on our polar curve. Now the key on this is recognizing that r of theta is the distance from the origin to the polar curve. So that means we're just trying to find the average value of r of theta. This is just an average value problem on r. So using our average value setup, we have 1 over the interval length, so 1 over radical pi minus 0, times the integral from start to finish here, so from 0 to radical pi, of the thing we're trying to average, so of r of theta, and then d theta. And this is just something we can plug in our calculator now. So here's the setup on the calculator. We have 1 over radical pi. I guess I could write minus 0, but I don't feel the need. There's my Math 9 integral. We have R1, that's this R function that we stored earlier, and pressing enter, we have an average value of 1 point, if we round this off, 580. For this part, they're telling us there's a line through the origin with a positive slope m that divides region S into two regions of equal areas. They want an equation that would actually solve for the value of m. So the key here is you have to set up essentially two different area expressions and set them equal to each other. One area is going to be going from 0 to whatever angle we're using there to get that line m. And then the other area, the other region, is going to go from the m, essentially, the m line, all the way to radical pi over here. So we have an integral from 0 to what? We need the limits of integration here. Well, we need an angle that represents this line with slope m. If I have a slope of m, the angle is just going to be the arctan of m, the inverse tan of m. Because if you plug in a slope to arctan, it gives you back the angle. So basic trig there. So the angle formed by slope m is arctan of m, whatever that is. It's a constant of some kind. So then I have an integral from 0 to arctan of m of, and now just 1/2 r theta, the whole thing squared. And now I'm going to say that that's going to be equal to an integral from arctan of m to the other end of my interval, to radical pi. And I've essentially got the same stuff in here, just 1/2 this function squared, d theta. And that's all I needed to do. I've got an integral, one or more integrals. I've got an m in there that I can solve for. So we're done with this part. For this last problem part, kind of the final boss battle of this, they're saying for k greater than 0, let a of k be the area of the portion of the region S here that's also inside the circle r equals k cosine of theta. We want the limit as k approaches infinity of a of k. So this is one of those where you're going to want to play around with the graph for a little bit. We have this circle, r equals something times the cosine of theta. Let's just graph that along with what we already have and see what that looks like. Now, if you're not really sure what to use for your k value, I'm just going to start with a k value of 1 and see what a basic circle looks like here. Let me do, let's say it happens if I do zoom fit, zoom 0. So we've got the original S area, and then this other piece here is a circle. Let me do zoom 4. I'm pretty sure I can see all this if I do zoom 4. So there we go. So we've got this little itty-bitty circle. Okay, now we want to know what happens as this circle approaches infinity. So let me go back, and I'm going to make my k value a little bit bigger. Let me make this 2. And then graph it again. There's S. There's k. Okay. Now let's make it 3 and see what's happening. There's S again. And there's our circle again. And again, this is only evaluated, let's see here. This is only evaluated from 0 to radical pi, so it's just this piece here. Now, let's make k a bit bigger. 3 is kind of underwhelming. Let's do like 9. See what happens. So there's S, there's my circle. So you'll notice as this circle gets bigger, you're getting more and more of this area. And at some point, let's make k really big. So I'm going to have to insert right here. Let me make this like, I don't know, let me just not super big. Let me make it like 39. And then graph it. There's S. There's our circle. So our circle, at some point, as we have a k value approaching infinity, the circle is going to be so kind of pressed against the y-axis that you're essentially going to be overlapping the whole area S, at least inside this first quadrant. The circle doesn't stray outside the first and the fourth quadrant. But within that first quadrant, you're going to take up all that space taken up by S at some point. So there was my series of pictures that I don't really have to draw to get credit, but I need to use them to kind of reason about this. As k gets bigger, the circle gets bigger, overlapping more of our region S in the first quadrant. That's what we saw in our grapher. So that means that the limit as k approaches infinity of this a of k, this is equivalent to the first quadrant area of region S. So that means we need the integral of the whatever gave us s from 0 to pi over 2, because that would give us our first quadrant. And now this is just going to be, again, 1/2 r squared d theta, so 1/2 r of theta squared d theta. This is something we can actually plug in our calculator now. So I'll be using kind of the same expression I used in part A, ironically, only now we're going from 0 to pi over 2 rather than the square root of pi. So this actually is going to give us an answer pretty close to what we got in part A. This answer turns out to be about 3.324, which is not too far off from our part A answer. So that tells us that it's a reasonable answer, but it is different enough that we need to write it down.